Welcome to Orbital Dynamics Part 42. This part is based on excerpts from the book, The Mechanical Universe. When we talked about Galileo's theories of relative motion, we defined inertial reference frames, frames of reference where the law of inertia holds. An observer in any inertial frame experiences the same laws of motion as in any other inertial frame and has no way of determining whether he or she is at rest or moving. Here we want to develop a mathematical framework within which to derive these ideas, both for inertial frames and non-inertial frames. Remember that non-inertial are those that accelerate relative to an inertial frame. We start with Newton's three laws. With these, we can derive Galileo's ideas in a clearer way. We can also deal with accelerated non-inertial frames. We'll do this by developing equations that transform motion from one coordinate system to another. Newton's three laws state, Law 1, a body acted on by no forces either stays at rest or moves with constant velocity. Law 2. A change in motion is proportional to both the force impressed and the mass of the object and takes place along the straight line in which the force is impressed. That's expressed by F equals ma. The first law is a special case of the second law where no force is applied. Law 3. Every action causes an equal and opposite reaction. A force, F12, is equal to minus F21. They're equal and opposite. Consider a reference frame called S. Let's say that this reference frame is fixed. Let's set up a simple offset vector R0. Then let's define the reference frame S prime offset from S by a distance R0. Imagine a train in the S prime frame and the platform in the S frame. S and S prime are fixed relative to each other. They aren't moving relative to each other. They're simply in different positions. What we've done is simply set up two coordinate systems with the origins offset by R0. Let's consider an object on the train depicted by this little red dot. The position R of the object in frame S is defined by this vector R. The position R prime of the same object in S prime is defined by this vector R prime. If we want to transform coordinates from one reference frame to another, we simply add or subtract the offset vector R0. That's defined by this equation, R equals R prime plus R0. This is simple vector addition. In this example, S and S prime are shifted diagonally. S prime could have been rotated relative to S, not rotating, rotated relative to S, or it could have been offset in a third dimension along a z-axis. The key point is that S prime doesn't move relative to S. Let's put the red dot in motion at a constant velocity. Mathematically, velocity is the change in position over the change in time. In frame S, that's expressed as dr dt, the derivative of position. The position vector moves with the red dot. The same would happen with r prime. Here's how we derive the velocity for frame S prime. First, substitute r prime plus r0 for r. The derivative of the sum is the sum of the derivatives. Here we do that expansion. r0 is a constant. dr0 dt is thus equal to 0. The velocity in frame S prime is thus dr prime dt. If S prime is simply offset from S, the relative velocities are the same. This is intuitively obvious. Velocity is the same in either reference frame, since S and S prime are fixed relative to each other. If you're on the train that's sitting at the station and you're observing the red object move, you'd measure the same velocity as someone on the platform is looking inside the train. Let's say that the red dot, rather than moving at a constant velocity, is accelerating. Acceleration is the change in velocity dv dt. We can substitute dr dt for v, and we get this, double derivative. This is another way of expressing that. To determine the acceleration in frame S prime, we'd substitute dr prime dt for v. Remember that dr dt equals dr prime dt, so we'll do that simple substitution. That can be expressed this way. Acceleration is the same in both frames of reference. If you're sitting on the train, observing the red object, you'd measure the same acceleration as someone on the platform looking into the train. That was a lot of formalism for a very intuitive concept. You'll see why, in a minute, we did this. Now let's put the reference frame S prime in motion at a constant velocity with respect to S. Here's our starting position. Vector R equals R prime plus the offset R0. Now we'll put S prime in motion. R prime is moved relative to R. Here's the new position vector in the S frame. The position of R equals, the position R of t equals R plus R0, the original position, plus V0 times t. We've added in a velocity component. Now let's put the red object in motion like we did before. In this case, both the object and the S' reference frame move at a constant velocity. That looks like this. Velocity, like we said before, is the change in position over time expressed as dr dt. Let's substitute the equation for r that takes into account the velocity of S'. R equals r prime plus r0 plus v0t. We can expand that into the sum of three derivatives. As before, dr0 dt is a constant. That results in this equation. dt dt of v0 is simply equals v0 since dt dt is 1. That reduces to this. The velocity in frame S' is dr prime dt plus v0. If you're sitting on the train, you'd see the red object move with velocity dr prime dt. If you're on the platform watching the moving train, the velocity of the red object from your perspective is dr prime dt plus v0. You'd add the velocity of the red object to the velocity of the train. We can show this geometrically with vector addition. This is the velocity vector of frame S'. If we add vector r to r0 and then to v0t, it results in r'. Acceleration is a change in velocity over time, dv dt, or the second derivative of the position. Here we substitute dr prime dt plus v0 for v. That results in the double derivative of r prime with respect to t squared plus dv0 dt. The velocity of v0 is a constant. dv0 dt is thus 0. The equation reduces to this. The acceleration in both reference frames is the same. That's a formal definition of an inertial reference frame. Both S and S' are inertial reference frames. The two frame S and S' are equivalent from the perspective of Newton's laws of motion that deal with forces and acceleration, even though the initial location of velocity of an object is different in the two frames. The laws of motion are invariant. This invariance is called Galilean relativity. Here's what things look like from the perspective of frame S'. This is what the world looks like if you're sitting on the train. If our frame of reference is S', then the vector r' doesn't appear to move. Instead, the frame S appears to move, and it moves in the other direction. Here's the velocity vector v of t. And here's the position vector from the S reference frame. The vector r still equals r' plus r0 plus v0t. The magnitude of the velocity vector in this case is negative. When you add all three vectors, you get r of t. Any measurement of position, distance, or speed must be made with respect to a reference frame. Galileo concluded that based on this premise of inertia, it's impossible to tell the difference between a moving frame of reference and a stationary one, without some outside reference to compare it against. This is referred to as Galilean relativity. Don't confuse this with Einstein's relativity. Have you ever been on a train at a station that was right next to another train? At some point, you notice the other train is moving. Then suddenly you realize it was you that was moving. In your frame of reference, you felt stationary. The train you were on accelerated so slowly that you didn't notice. From your frame of reference, the other train was moving. Someone on that train would have experienced the opposite, that you were moving. Galileo argued that it wasn't that one of you was moving and the other wasn't. The other train, and the entire Earth for that matter, was moving relative to you. You were moving relative to the other train. Galileo asserted that both frames of reference were valid. In section 32, we talked about compound motion. I showed you this animation. The train moves with a horizontal velocity vx0. The ball that's dropped by the man standing on the train car travels at v0 relative to the platform. From his perspective, the horizontal velocity is 0, which means it falls straight down. The ball that's thrown backward by the man on the train travels at a velocity minus v0. The motion of the train and the ball cancel out. To someone standing on the platform, the ball appears to stand still. In this animation, we depict a ball being dropped on a train traveling at velocity vy0. The panel on the left is from the perspective of the platform. The panel on the right is from the perspective of the train. The green dot that moves horizontally in the left panel depicts the horizontal motion of the train. By Galilean relativity, the same laws of motion apply to the ball in both frames. The horizontal motion is governed by the law of inertia. The force along the x-axis Fx equals the mass of the object m times ax, the acceleration along the x-axis. Since the train travels at a constant velocity, there is no acceleration along the x-axis, so the force equals 0. From the perspective of the platform, the ball travels along with the train at a constant horizontal velocity vx0. The vertical motion, however, is governed by the law of falling bodies, where ay equals g. That accounts for both balls falling to the ground at a faster rate over time. They both fall at the same rate. The trajectory does not look the same in both frames. In frame S', in which the train is at rest, the motion is straight down, whereas in frame S, the trajectory is parabolic because the ball shares the inertia of the moving train. In frame S', where the train's at rest, the formula for horizontal motion is expressed as x' equals 0. The formula for vertical motion is expressed as y' equals vy0t minus 1/2 gt squared. Vy0 is any initial velocity. In this example, the ball starts at rest, so the initial velocity is 0. Hence, y' equals minus 1/2 gt squared. The trajectory is parabolic in frame S because in that frame you experience both horizontal and vertical velocities together. Let's derive formulas for this frame. From the platform perspective, the horizontal component is expressed as x equals x' plus vx0t. That says that the horizontal position x is the sum of the position x' in the frame of reference of the train S' plus the velocity of the train vx0 times t. We're simply adding the horizontal velocity of the ball to the horizontal velocity of the train to come up with the horizontal velocity of the ball as perceived by an observer on the platform. Substituting x' equals 0, we get that the x-coordinate in the S frame is vx0 times t. That's the horizontal velocity of the reference frame S'. The vertical motion is the same in both frames. Y equals y'. Y then equals vx0t minus 1/2 gt squared. The two equations for x and y result in a parabola. Y equals 1/2 gt squared with no vx0t. The two equations for x and y result in a parabola. Here we deal with non-inertial reference frames, frames of reference that accelerate. S' is accelerating in relation to S. The best analogy for this is a rocket ship with its engines fired. Note the red object inside the spaceship. S is an inertial frame, and it's at rest relative to u. S' is no longer an inertial frame of reference. If you were an observer in frame S', you'd feel a force acting upon you that you wouldn't feel in S. Recall that in section 32 we derived an equation for position that takes into account acceleration. Over time t, the position of r in frame S of an object in S' is the sum of r' plus r0, the offset, plus v0t, the initial velocity of frame S', plus 1/2 a0 times t squared. That accounts for the acceleration of frame S'. The position r is from the perspective of the S reference frame. You're looking into S'. Let's say now that an object is moving in S' at a constant velocity. Notice the spaceship is accelerating in frame S', and the red object is moving with a constant velocity relative to the spaceship. That velocity has changed the position over time. We can make the substitution for r. That expands out to this. dr dt is 0, and dv0t dt is v0. We're left with this. 1/2 a0 is a constant, so that can come out from within the derivative. The derivative of t squared is 2t. That results in this. The velocity in frame S takes the velocity there is in frame S', the r' dt, and then adds the initial velocity of the frame S', v0, plus the acceleration of S', a0 times t. The velocity of the object with respect to the spaceship in frame S' is constant. The velocity in the frame S, however, is now time-dependent because of the last term, a0t. That means that the velocity changes over time. That makes sense since there's a force acting on the S'' reference frame, namely the rocket engines. Let's now say that the object is accelerating within S'. Acceleration is the change in velocity. That's expressed this way. That results in this equation, dv0 dt, and it's 0 since v0 is a constant. dA0 dt is a0. That reduces to this. Acceleration in frame S is the acceleration within frame S', plus the acceleration of S'. We can express the acceleration in frame S more simply. It's the acceleration in frame S', plus the acceleration of frame S'. We can derive the acceleration a double prime as the difference between the acceleration in s minus the acceleration of s double prime. According to Newton's second law, the force experienced by a body in frame s is F equals ma, and the force F double prime experienced in frame s double prime must satisfy F double prime equals ma double prime as well. If we subtract F equals ma from F double prime equals ma double prime, we get this. Let's put F on the other side of the equation. Let's substitute a minus a0 for a double prime. That expands out to this. There's a plus ma and a minus ma that cancel. F double prime, the force exerted upon an object inside the spaceship, is the force in the inertial frame, F, plus the mass, times the acceleration of the s double prime reference frame, the spaceship. These forces differ by ma0. The extra force, little f, equals minus ma0, experienced in the accelerated frame is called an inertial force. It's often referred to as a pseudo-force or fictitious force, though there's nothing fictitious about the effects of such a force in an accelerated frame. To get a better idea of this, let's put the red object at rest in the spaceship. Here the spaceship accelerates. To us, in the S reference frame, the object remains at rest while the spaceship accelerates forward. The people on the spaceship have a different experience. They experience a force acting on the red object equal to minus ma0. It looks to them like the red object falls to the floor with an acceleration a0. From our perspective, we know that the red object's not moving. Within the spaceship, it's apparent motion. That's why it's referred to as an inertial or pseudo or fictitious force. Let's show this vertically. Here's what the motion looks like from an inertial reference frame. If you're on the spaceship, here's what that motion looks like. Coincidentally, here's acceleration due to Earth's gravity. Played side by side, these two motions look identical. That's the basis of Einstein's equivalence principle that we'll talk about later when we cover general relativity. The simplest case of inertial force occurs in frames that accelerate at a constant rate, a0, in a straight line. Consider first a man in an elevator. If you put him on a scale, he can measure his weight. Now accelerate the elevator upward at a constant rate, a0. The inertial force is F equals minus ma0. The man with mass m experiences both gravitational and inertial forces. We'd express that as F double prime equals m times g plus a0 in the frame of the elevator. The scale will register a higher weight. If the elevator were going downward, the force would be m times g minus a0, and the scale would register a lower weight. An elevator in free fall is an extreme example. Here the elevator is acted on only by gravity in an inertial frame. The elevator has acceleration a0 equals g relative to the inertial frame, so the net force on the man in the elevator is F double prime equals m times g minus a0, which equals 0. Thus, the man is weightless, and the scale will read 0 pounds. Weightlessness occurs not only in a body falling straight down, but also in orbiting satellites. In a frame fixed with respect to a satellite, the satellite is weightless. This leads to dramatic and visible effects. If you are in an orbiting spaceship, things float inside, and astronauts are weightless. If the acceleration a0 is in a different direction than the gravitational force felt in an inertial frame, the apparent direction as well as the magnitude of gravity is shifted in the accelerated frame. Consider a glass of water in an airplane. Let's depict this graphically. The force of gravity keeps the water in the bottom of the glass, with the level of the water normal to the gravitational acceleration. At takeoff, the plane accelerates horizontally in the x direction. The sum of gravitational and inertial forces on the water is F double prime, which equals minus mgk minus ma0I. The net effect is the water in the glass tilts. The surface of the water takes up a position normal to the force F double prime. The water can be described as experiencing an effective g of magnitude F double prime divided by m directed along F double prime. Let's review these relative motions. On the left, when we merely displace the origin of frames s and s prime, the shapes of trajectories, as well as the forces in s and s prime, are the same. The positional coordinates are different. We transform from one coordinate system to another with this equation. Velocity, acceleration, and hence the forces are identical in both coordinate systems. In the middle, when s prime moves at uniform velocity with respect to s, trajectories look different in the two frames, but the forces and accelerations are identical. Both frames are inertial frames. There's now a time-dependent component to the positional transformation equation. We transform velocities with this equation. Acceleration and hence forces are identical in both coordinate systems. This formally is what it means for both frames to be inertial. The displacement case is the special case of this inertial case. On the right, when s double prime accelerates relative to s, the forces and accelerations now look different. The positional transformation has a time component, like in the inertial case. So does the velocity component. Accelerations and forces are no longer identical. They're different in each reference frames. If you conduct a physics experiment in frame s double prime, you get a different result than if you did in frame s. We use one set of transformations for simple displacements, another for inertial frames with relative motion, and a third for non-inertial frames that accelerate relative to each other. In all cases, the form of the fundamental law, F equals ma, remains unchanged. Galileo asserted that the laws of physics are the same in all inertial frames. He described a ship traveling at a constant velocity without rocking on a smooth sea. Any observer doing experiments below the deck would not be able to tell whether the ship was moving or stationary. Today, one can make the same observations while traveling in an airplane or a train with constant velocity. Galilean transformations transform coordinates of one reference frame to another. They differ only by the constant relative motion between them. One item of note, the transformation equations, although apparently obvious, break down at very high speeds that approach the speed of light. Einstein resolved this in his theory of special relativity.